Hi guys, welcome to my 12th episode of Love the Byte series. My name is Samuel Kamochu, a telecoms and a software engineer, co-founder and the lead pay setter at Meliora. In this episode, I want you to appreciate how to manipulate bits and bytes, or rather what we call bitwise operations in Java. So I know you've done decimal to binary conversions, but allow me to show you an easier way to do it. So let's take the place values of the binary numbers and let's look at a number 38. The key idea is to look at what fits into 38, and by this case we have 32, and 32 leaves us with 6, and that 6 we have 4 that fits into it, and then eventually we have 2 that remains, which we have 2 that fits into it. So in total we get 38, and for us to convert this thing into a binary number, where there is a 32, a 4, and a 2, set those bits to 1, and the rest set them to 0. So that gives us the binary number. Let's apply the same concept on 23, and 23, definitely 16 is the first number to fit in 23, and you're left with 7, then 7 you have a 4, a 2, and a 3, and that gives us 23. If you want to convert this into binary, set 16, 4, 2, and 1 as 1, and the rest as 0. So we basically have that as the binary representation of 23. So we are going to use these numbers to illustrate bitwise operations in the next few slides. So let's look at the logical AND, and we already know the truth table for the logical AND. The symbol is 2 ampersands. Let's look at the bitwise AND. The symbol is a single ampersand, and the key idea is when there is a bit set to 0 and B is 0, A is 0 and B is 0, we get a 0, and definitely we'll only get a 1 when the 2 bits are set to 1. So how do we illustrate this? Let's evaluate 38 and 23, and this is bitwise operation. So the key idea is we'll get the place values. We already know the binary representation of 38 and 23, and here we are now going to apply the bitwise AND to do this. So the answer will be 1 only when 1, A and B are set to 1. So we have 2 bits which are set to 1 in the result, and we know that the first bit, the place value is 4, and the second bit, the place value is 2. That gives us 6. So in other words, 32 and 23, the answer is 6. You can validate that using Java, and I've just complicated the program a bit by representing A as 38 and 23. Definitely these are integers, but since they are less than 1 byte, they can fit in a byte. So the key idea is we have A and B, and you can see I have done a typecasting because in Java, when you do mathematical computations with numbers that are whole numbers, then what we get is integer as an answer. So if you have to typecast, if you have to store that number in a byte, then you need to typecast into a byte. And what it does, it discards the 3 bytes in an int, and it leaves us with the only 1 byte, which is the least significant byte. So I hope that doesn't confuse anyone. And the other idea is we already know that these 2 numbers, 38 can be represented as this in binary, and 23 as indicated on the screen. So the key idea is 0010 is 2 and 0110 is 6, because this is a 4 and the other one is a 2. You add them, you get a 6. Same case, you can actually evaluate this as 1 and this is 7. So we do the printing and we are supposed to get the same answers because A and B is equivalent to X and Y respectively, only that they're represented in decimal and hexadecimal respectively. So let's look at the logical OR, and the key idea here is we have the truth table. I'm not going to repeat this, but you already know. And the bitwise OR is wherever there is a true, you replace with a 1, and whenever there is a false, you replace with a 0. And for us to evaluate 38 or 23, we have to get the 2 numbers in binary, again, just like we did earlier. And here we are going to use the OR side. Anywhere there is a 1, we get a 1. And you can see that 32 becomes a 1, 16, 48 plus 4, 52 plus 2, 54 plus 1, 55. So the answer is 55. And when you do that, you get 55. So if you print the same in Java using similar code as we had done before, you can see that it's 55 because A and B and X and Y are technically the same, only that they're represented in different number systems. So let's look at the logical XOR or the exclusive OR and the bitwise XOR. So the truth table for the logical OR is it's always false if both A and B are the same. So false, false gives us false, true, true gives us false. And it's the same case with bitwise. 1, 1 gives us 0, 0, 0 gives us 0, otherwise the rest are 1. 23, that is. So we do the same, we get the numbers, and now we use the XOR. Here you need to pay attention. Where there is a 1, we get a 1. 1 and 0, we get a 1. 0 and 1, we get a 1. But anywhere there is 1 and 1, we get a 0 and a 0. Please note these two bits because it's because of the XOR that they have become 0. So if you look at this number, it's 32 plus 16, 48 plus 1 becomes 49. And that gives us 38 XOR 23 gives us 49. So in the event you run this code that I've presented here, it's going to print 49 and the explanation is obvious. So let's look at logical NOT, and this is a slightly different from the others, and the bitwise NOT. So when we have false, the logical NOT is true, and when you have true, it becomes false. Same case. When you have a 0, it becomes 1, and when you have a 1, it becomes 0. And that's what we call the ones complement. Now, here we are going to teach you something called 2's complement, and the 2's complement of A is negative A plus 1. So this is a very important concept because this is how computers represent negative numbers. If you remember, we say Java does not have unsigned data type, so everything is signed. So if you have a positive number and a negative number, we must use the 2's complement to represent the negative numbers. So let's look at this 2's complement. The idea is you want to present a negative number in such a way that if you have a positive 5 and negative 5, when you add them together, the result is 0, which is known to be true. But then let's see how we are going to do this with bits. 5, which is our A, if you write it in binary, is 0, 1, 0, 1. And the complement of A is what you're calling negative 5. And we are going to take the most significant bit will be consumed as a sign bit. So if the leftmost bit is set to 0, we already know that it is a positive. And when it is set to 1, we know that it's a negative number. In this case, 0, 1, 0, 1, if we consider the 4-bit number, this is a positive number. Now, if you want to convert this positive number into a negative number, first you need to set this 0 into 1. That's step number 1. So we have not changed the other bits, which we are going to manipulate instead. So then after that, you get the 1's complement of the remaining bits. And 1's complement is you have 1 becomes 0, 0 becomes 1, 1 becomes 0. And you have 1, 0, 1, 0 as the number that we get after the 2 steps. Now, the third step is we add the 1 to a result. So we are going to add 1 to the result, and definitely we are going to get 1, 0, 1, 1, the 5 complement, or what we use to represent the 2's complement of 5, which we use to represent negative 5 in the computer. Now, let's take an example of addition. Let's take 5, and we know the value is 0, 1, 0, 1. Let's take negative 5. We know the value is 1, 0, 1, 1 in 2's complement. So if you add the two numbers, then definitely you'll get 1 plus 1 becomes a 0, carry 1. Then the carried 1 plus 1 becomes a 0 again, carry 1. Then you have 1 plus 1 again, 0 again, carry 1. And then you have 1 plus 1, then you have a 0, carry 1. In 2's complement, if you do the addition, you discard the final carry. So the answer becomes 0. That way we've been able to do negative 5 plus positive 5, and the answer becomes 0. So this makes addition of negative number very easy because all you need is to represent them as 2's complement, and using one adder in the ALU, you can do both negative and positive number computation. So if you want to subtract, you don't need another circuitry in the ALU. So more on 2's complement. Now, if you use 2's complement, this brings a bit of complications, especially if you're dealing with signed data types. So if you look at this byte stream, this is a common byte stream, which we saw sometimes back. When you convert it into decimal, it gives us the IP address. And we want to look at this and say that these are 4 bytes, each byte representing a number that is 0 to 255, which is unsigned. But now the challenge is if you have C0, which we know is the 192 as the IP part, but if you have it in Java, then we get into a problem because when you print this value, you get a negative 64. And why is this the case? Because C0 is represented as C is 12. So we have 1, 1, 0, 0, 8 plus 4 becomes 12. And then the last 4 bits are 0 because the 0 becomes 0, 0, 0, 0. Now, if you look at this, let's compare with the complement of 64. So 64 is 0, 1, 0, 0, 0, 0, 0, 0. Now, if you do the 2's complement, you basically change the first bit into 1. Then you find the 1's complement of the other bits, which gives us this. Then you add 1 and you get this. So you can see that C0 is actually the 2's complement of 64. And that's why it prints negative 64. Now, how, if you are writing a program to actually decode the IP header, how do you get 192 out of this? So there are 2 options. The 2 options is you either convert the byte into an unsigned integer, and the basic idea is to ensure that there are more bits to the left of the number, and the bits are set to 0 so that the leftmost bit becomes 0, and that ensures that the number represented there is a positive number. Or you can actually AND with a byte, all bits set to 1. And if you AND, we said that when you AND with a value like this one, then it becomes integer computations. And that way, you'll have extended the 8 bits to 32 bits, and the bits on the left will all have zeros, and that will make your number positive. So technically, if you look at the Java code to illustrate that, so you have this number that you represent as this. If you print, definitely this is negative 64, as you can see here. But if I want to print 192, I need to add more bits to the left so that the leftmost bit becomes 0 and the number will be treated as a positive number. So all I do is I have to change from using a byte to an integer because the integer uses 4 bytes, and I'll ensure that I mask it. I AND it with a mask that has the 8 bits set to 1. And when I print this, the answer will be 192. There is also an inbuilt function within the byte class within Java, and you can say to unsigned int, and it will give you an integer, and it will give you the same value. So this is the complication that comes in when you're dealing with the 2's complement. Now, how do you apply these things that you're learning? So I've shown you how to deal with bitwise operations, and I can tell you for sure, this is a section of a protocol document, and protocol, I'll leave you to guess which protocol it is. And the key idea is that I have 32 bits. If you look at this, this is 4 plus 6, that's 10, plus another 6, that's 16, plus another 16, that gives us 32 bit. And when I capture the network trace, these are 32 bits of data, and they're represented as nibbles, 80180200. We already know that 80 is a byte, 18 is a byte, 02 is a byte, and 00 is a byte. So let's break this down and let's decode it. So if you look at the 16 bits to the left, they are representing the header, the result, and the flags. Let's call these things flags. And then the 16 bit to the right are the window size. So the window size is a number. So all we need to do is to evaluate. Here we will evaluate the bits because we need each bit. And here we are going to convert it into decimal number. Sorry, this is not binary. So once we convert into the decimal number, we know that the window size is 512. But here we have converted into bits because we want to split this again. So we group 4 bits, which is the length, and the next 6 bits is the reserved bits, and the other 6 bits are basically the flags. So essentially, these are the flags. And we're interested in the flags. We know that the second flag, which is acknowledgement, and the third flag, which is push, is set to 1. So we can see that ACK and push are set to 1. So if I take the Wireshark view of the same, we can see that the reserved bits are all here. These are the 6 reserved bits. And you can see that the agent, which is the flag, which is set to 0, then you have acknowledgement set to 1, and the push set to 1. And we have the reset and the sync and fin set to 0. So basically, we have been able to decode this thing with our knowledge in our head. But now, if you want to decode these things, you must use bitwise operations. And in this case, there is a concept called masking, which you will learn probably in the next episode. So the second thing is, if you're implementing binary protocols, this is like we have just demonstrated in the previous slide. You're implementing binary protocols, you must have this knowledge. And we will have a bonus episode on a hands-on session. And my objective is to ensure that you actually get to decode a whole protocol header in the hands-on sessions. So I'll give you an assignment. I know some of you are like, wow, yes, I know. I've been working very hard, and it's for you to also work hard. And I'll leave you to read left, right, shifting of bits. And I know that you'll do it. And if you don't do it, I know God is watching. So please be responsible. And that brings me to the end of this episode. And if you found the concept interesting or helpful to you, and you believe it can be beneficial to someone else, please share with them. Also, feel free to like, comment, and subscribe. And as always, ensure that you turn the notification button on for us to notify you of the next episodes. Thank you very much, and see you again in the next episode.